Welcome back, everybody. We're going to talk about graphing systems of equations, and we're not going to do much work ourselves. We're going to let Desmos, the famous graphing calculator, free and available to anyone online, we're going to let Desmos do a lot of the work for us. So the point of a system is we have two linear equations here. We're going to graph, and then we're going to see where those lines intersect. So starting out here, see we have the line y equals x minus 5, y equals negative x minus 7. Let's put that on Desmos, and again the website is desmos.com/calculator. Bring this down here so you guys can see that, desmos.com/calculator. And we're going to put those two equations I had y equals x minus 5. Notice how type that in and it graphs instantly. We can see that right there. And here's the other one. Just go to number 2 and let's graph the other one. Y equals negative x minus 7. I can't see it here. Let me smooth the screen up. There it is. If you click right where they intersect, it'll tell you, there it is, negative 1 and negative 6. Negative 1 comma negative 6 is where those two lines intersect. Go back and let's try another one here. Alright, we have this one, another system, y equals 2/5 x minus 5 and y equals negative x plus 2. So we're going to put that in Desmos here. 2/5 x minus 5 and negative x plus 2. It's real easy just to clear those out and type over them. So now we have two new equations. As you can see, if I click right here, I see the point of intersection 5, negative 3. Let's hope you guys can see that. 5, negative 3, just like that. And I meant to write them on the lines here so you guys can see. There we go. And something to point out too, as in later videos we'll talk about solving without graphing. This is the x coordinate, this is the y coordinate. If we substitute this 5 in for both of those x's and this negative 3 for both of the y's, it'll make both equations true. This number set solves both equations at the same time. Let's look at another one here. Now we're going to actually, we're being asked to classify this system. All right, in order to classify it, we kind of have to see what it looks like. So x minus 3y equals 4, and y equals 1/3 x plus 1. We're going to graph that. Notice the nice thing about Desmos, it doesn't have to be in what they call slope-intercept form. You can just type it in, no matter how it looks, and it's going to graph it. So there's the line x minus 3y equals 4. And then here's y equals 1/3 x plus 1. All right, now looking at these two lines here, as you can see, they don't intersect. That means they are parallel lines. There is actually no solution. All right, for this problem. So we'll type that out, no solution. And when it's no solution, we call that an inconsistent system. No solution means inconsistent system. You can see that there. If you're inconsistent, well then there must be a consistent. Okay, if no solution means inconsistent, and I may want to point out they make parallel lines. So there must be something called a consistent system. Yep, and that means the two lines intersect. And then there's 2 degrees of consistency. There is what's called consistent dependent. And then there is also something called consistent independent. And then here's the difference between the two. If it's consistent dependent, that means it's the same line sort of on top of itself. And so in theory you have two different lines touching each other an infinite number of times. Consistent dependent systems would have infinite solutions. Consistent independent means they intersect. They intersect in one place. So there's actually one solution. The first two examples we showed, I think, would be called consistent independent. All right, and again, we saw this looking at the graph. See how they are in parallel lines. They never intersect. Let's look at another example here. I'm going to talk about systems of equations a little bit differently. Let me get this deleted here. So it says, what's the solution of f of x equal to g of x? Now, f of x, g of x are notations for function notations. We actually have two different systems here, two different lines here. We actually have an exponential here. Notice it's 2 to the x plus 3, and then we have a linear negative x plus 6. And what is the solution? We want to see where those intersect. So we're going to graph those. Let's graph this first one here, and I'm going to delete both of them so we have a nice clean slate to work with. Here's the first one, and Desmos allows you to write it in that function notation. 2 to the x, and I did a little shift 6 to get that caret, plus 3, and then I'm going to do g of x is going to be equal to negative x plus 6. All right, kind of hard to see. We didn't see that graphed. All right, there we are. The blue line is the exponential. Notice how that exponential looks. It kind of goes, it's in a curve, upward curve, and then there's the linear green line, negative x plus 6. And if I click right there, that's going to tell us where the intersection is. Now, they intersect at 1, 5, but the question is asking where do they intersect? The where question, or the what is the solution? Yep, what we say 1 and 5. Let's double check that again. 1, 5. Yep. And we say the solution to f of x equals g of x. That is the point of intersection. But we really want to focus on a question like this: is x equals 1? That's showing where it is. X equals 1 solves both systems. It makes both of the y values, or f of x, g of x, be the same value. So it's kind of like saying, where does 5 equal 5? Where do the y values equal each other? They equal each other when they both are 5, and that's occurring here at x equals 1. All right. Look at another one here. It's a little more complicated. How about the solutions to negative 3/4 x plus 2 1/4? And the other function is g of x 1/2 to the x power plus 1. Okay, we will plug those in here. Let's go ahead and exit out. All right, here's our new one. F of x equals, all right, negative 3/4 x plus 2 1/4. There's 1. Let's get the other one here. I think I had an exponential. G of x equals 1/2 raised to the power of x, and then we're adding 1. All right, now as you can see here, they intersect twice. So yes, we could have two intersections. I'll click on that to mark it. I'll click on this to mark this. And we're kind of interested, we're really interested in where they're happening on the x-axis. And look at the x-coordinates here, negative 1 and positive 1. That's where the intersection occurs. That's how we're going to solve this and say the solution. It occurs at x equals 1 and x equals negative 1. Those are where those solutions occur. Those are, in fact, the mathematical solutions of the x-coordinates. It's where the y-coordinates equal each other. All right, and the next one takes this concept of finding solutions to systems. We don't have the luxury of a graph here. We're not going to look at a graph. We can if you want to. There's the functions f of x equals 0.25 to the x power, g of x equals negative 0.75 x plus 1. What are the solutions? We want to see where the y-coordinates are the same. Looking at these values here, where are the y-coordinates the same? And the y-coordinates are the same at, if you see here, let's highlight this, 0. Let me get a highlighter here. 0 and 1. I know that because I see the x and y values the same there. The y values are the same here. This y value is the equivalent to this y value. This 0.25 is equivalent to this 0.25. That's why I know x equals 0 and x equals 1 for these systems. So it's kind of the same concept, it's just we have a table of y values rather than an actual graph to look at. Alright, let's try another one here. Best decimal approximation for -2/5 x minus 2 and y equals 5x plus 1. We're going to put that on there. Let's exit out our values here. Y equals -2/5 x, and you got to be careful how you type it in. I'm going to arrow over, just put that there, say minus 2. There's our line. You see it down there at the bottom. Let's get that other one. Y equals 5x plus 1. Do we see that intersection? No. I'm going to move it up here so we can. There we go. Okay, and Desmos will give us a decimal. Notice it's not a nice whole number. It's a decimal approximation. -0.556 and -1.778. Alright, again, that's -0.556, -1.778. Put that on our answer sheet here. And if we needed to round, we certainly could. And what did they say it was? -1.778. There we go, a good decimal approximation. We're going out to the thousandths place on this. Now let's look at one where we take a break from Desmos. What's the best approximation to the solution of the system? It might be off a little tiny bit, and look at the increments on the x and y axis. We see it right here. It might be off a little bit, but we can look at that and say the x coordinate seems to be -5. The y coordinate seems to be 6. We can say the approximate solution, we may not know exactly, maybe if we zoomed in a whole bunch, but we could see a good approximation for this would be -5, 6. We're looking for where they intersect. Alright, and let's try one more, the same type of problem here for Desmos. Best approximation, we'll round to the nearest whole number. 12x plus 5y equals -29, x minus 3y equals -1. Let's go back over here to Desmos and do that. We said 12x plus 5y equals -29, and the other one, x minus 3y equals -1. There we go. I see our point of intersection right here. Now we can see the decimal. Desmos does a good job, thousandths place, but I would say -2, -0.5, -2, -0.5, just rounding it. It would round, maybe -0. We would say 0 for the y coordinate, but let's just go ahead and say a fraction. -2 and -1/2. That's a good approximation. It's not the exact, but it's a good approximation. Alright, I hope these problems helped you understand systems a little better, and also using the great website Desmos.com. Thanks for watching.